Dr. Jorge Bueno Morón, apologies for the presentation.
Yes.
So finished his PhD at University of Amsterdam 10 years ago, and then joined Avantium. During the past 10 years,
yes.
Worked on sugar chemistry and biorefinery topics, and here today will present some of his results on furanic derivatives. Six.
Exactly. Thank you very much for the introduction. So it's the last talk, so I will try to keep it brief, but yet interesting. So indeed, my main focus in Avantium, which I'm going to speak now, is a biorefinery. And I'm going to show you like a tale, like a story of how we are trying to really make an impact in the world and to convert lignocellulosic sugars and waste materials into bio-based plastics. So this is Avantium, in case you never heard of it. We are a small company, 200 employees or so. It's been more than 20 years operating, but well, basically our mission is to really make an impact. We are one of these very, very enthusiastic companies that really try to do something that the society can benefit. And this is in a nutshell the presentation. So basically, this is like the last point of the presentation, which I put in the beginning to have like a better view. I'm going to explain you how we can convert renewable feedstock, in this case forestry residues, but also waste materials like cotton textile. But I cannot go too much into detail because I want to keep to the time. But basically, we divide it in two phases. The first part is the sugar recovery, how we get the sugars out of these materials. And the second part is the furanic conversion, because it is connected to our main core of the company, which is make bio-based plastics. Today we have seen a lot of things that you can do with these furanic compounds. I'm going to focus on how we get this, what is the technology that we are deploying, and we have already a pilot plant, and we are, well, in conversations, we are exploring the next year to come to go to the flagship and commercial plant. But the PEF, the alternative to PET, which is with a furanic compound in the middle, with an oxygen, the furanoate, that is the main core of our technology. So I don't need to go through this. This is the structure of the tree. This is how we started. We focused on lignocellulosic biomass because we wanted to make use of the cellulose and the hemicellulose mainly. And this is the technology that we started, well, 10 years ago. This was the first stage. At the beginning, what we were doing is taking the wood chips, the residues of particularly the north of the country, of the Netherlands, and we were using ACL, aqueous solutions, at room temperature and ambient pressure to extract all the sugars in separate steps. And this was the first breakthrough to make it commercially available or to make it economically interesting, because we could separate the hemicellulosic sugars from the cellulosic sugars, and at the end of the process, what we will have is basically the lignin. This is already a technology that happened in the 1920s. After the First World War in Germany, there was such a scarcity of food that Bergius, the person that you see here in his laboratories, he thought that he could extract the sugars from the biomass to end up producing food. So this was a dream that did not come through, but the amount of development that he did in that field, specifically in ACL at room temperature and ambient pressure, is impressive. It's really impressive. So we took this inheritance from the 1920s and we said how we can do it now, but instead of food, on bio-based materials. So we started with the first design, which was to separate the hydrolysis in two steps. This is important because I'm going to go through the story. And the first one is two stages. So we found out that using different concentrations of ACL at the same ambient pressure and room temperature, we could selectively hydrolyze either the hemicellulose, as you see here, the hemicellulose hydrolysis, and then this acidic solution would contain the xylose, mannose, galactoglucose, the sugars that are usually in the hemicellulose. And then by increasing the acid concentration to 42 and above, again, aqueous and ambient pressure and temperature, you could recover the more calcitrant part, which is the cellulose. And you would have a pure glucose stream. In the end, we would have a lignin pelletization. This was the structure of the idea, but this didn't work. This is one of the stories that this didn't work. Because Separating the sugar solutions is very good at lab scale, but when you go into detail and you go into bigger scale, you start to see that all these sugar solutions start to mix with each other. And again, our core of the business was to separate the sugar solution. So if we cannot separate the sugar solution, we have to do something else. So the something else was the furanic production. At the beginning, we thought, well, if we use HCl above 42%, we can hydrolyze absolutely everything. And what is left is the lignin. Now there is no problem. There is no separation. There is no mixing up. We have all the sugars in solutions, and what is left is the lignin. So this is the next stage that we started 5 years ago. Okay, we have a mixed sugar solution. We are very good doing this. We have a pilot scale. What is next? Well, with these sugar solutions from the lignocellulose, we saw that there is a correlation, or there is something in common with all these sugars in solution, and it's the amount of carbons. So we have C6 sugars that if we dehydrate, basically at at 80 degrees, if you have your sugars, your 6 carbon sugars in HCl, you can produce 5 chloromethyl furfural. And what happens with the 5 carbon sugars, like for instance, xylose and aminos? Well, in similar conditions, the dehydration produces furfural. This is a two-step process for the chloromethyl furfural. I will go a tiny bit in detail, but as you see, as you can imagine, first it goes to hydroxymethyl furfural, and what happens, there is so much HCl in this solution that you produce the nucleophilic substitution and you produce the chloromethyl furfural. And then why chloromethyl furfural from all the molecules, compounds, and furanics that we could produce? First, because we already have a lot of HCl in our mixed sugar solution, and second, we found a way to connect it to our beautiful plastic bottle made out of PET. And this is through the production of MMF, methoxymethyl furfural. We have a separate plant, a flagship plant that is going to open in 1 month, after 2 other pilot plants, that we are aiming to commercial scale of producing PEF through methoxymethyl furfural. We usually produce this from glucose and fructose, but we have to buy the glucose and we have to buy the fructose, and then we dehydrate it and we produce MMF. In good yields though, but this is not so sustainable. We are buying the things. So this was an excellent solution to connect lignocellulose forestry residues, important the residue part of it, to produce chloromethyl furfural, MMF, and PEF. And why furfural? Well, what do we do with the furfural? Well, I think in this conference we have been seeing a lot that the furfural, the market size, and all the applications that it has is just amazing. So it's for us would be a side product, but actually it is not a side product anymore when you do the techno-economic assessment of the whole thing. So this is the mechanism of formation, very quick, very simple. We use biphasic systems. We use biphasic systems because we have our sugars. If we go from the bottom, this is our feedstock. What happens, I'm going to say what happens to each of the sugars, but actually everything is in the same pot or reaction because we have all the sugars mixed. What happens to the xylose and the arabinose when it's in the presence of HCl and we decide to heat it up, the solution, to 80 degrees? Well, it will produce furfural, but if we would just do that, furfural would decompose in time. But this is a trick, also based on literature before. They added chlorobenzene, or an immiscible organic solvent that has affinity for this type of compounds. So, we started doing small tests, but the yields were amazingly good. Basically, what we were finding out is that in the organic phase, we were finding furfural in high yields and concentrations. And what is left in the sugar solution, well, basically is the acids. The acids and a little bit of the composition of the products for accounting for the amount that we were missing of the furfural there. And this was happening exactly the same for the feedstock containing the 6 carbon sugars. But in this case, a tiny bit more complex, just basically because you need a nucleophilic substitution. First, you have your dehydration to HMF, and of course, there's a lot of HCl, I already said. There's an equilibrium, but it's more displaced to the CMF. The trick here, again, is the organic phase. And the organic phase extracts the chloromethyl furfural up there, and then it can still go to hydroxymethyl furfural. This was something that we were dealing with it. But the amount of water and HCl on the organic phase is very small, so mostly we were getting CMF. So this is in a nutshell combining knowledge that we had from the 20s and knowledge that we had from the 80s. In the 80s was the use of biphasic systems. They were not so focused on obtaining a chloromethyl furfural like we are now, but combining these two technologies, it really worked. So we also, of course, now I go to the mixed sugar solution because I explained what happened separately, but in our mixed solution, as because the mechanism of formation is different, that means that the conditions are going to also be different. For the chloromethyl furfural, it requires more energy because it's not just dehydration, it's dehydration and nucleophilic substitution. For furfural, it's much quicker. So this is in a nutshell what happens during the reaction time. You see at the bottom. Well, we're heating our solution 80 degrees, and as you can see, first the furfural goes to very high yields, but then CMF requires a little bit longer, is the light yellow bar. It requires a little bit longer, like 4 hours to get to yields above 90%. Well, you can see the problem. If we go to the 100% or 90+% of CMF, the furfural is already declining. So this is something that is process operation, and we need to optimize, of course. But we could see that for the same conditions, which is 80 degrees, not the time, but 80 degrees acid concentration, the sugar solution coming from the same feedstock, all the hydrolysis is all the same. We need to tweak the temperature and the time. And then we also saw that this is for furfural production. We saw that you can produce furfural in high yields at lower temperatures than 80 degrees. So this is one idea that we are applying. Basically, we could first start with lower temperatures than 80 because for CMF, we need 80 degrees. But for furfural, as you can see, the yellow bar is 70 degrees. Okay, it takes a little bit longer, but it can reach high yields. And the other bars, we could not see it here, but you have to believe me in this one. It gets high. You have to read it. For 60 degrees, for 50 degrees, it takes too long. So this was a very good idea. Basically, we thought, well, first we use a temperature that the CMF is not converted, so the sugars, the 6-carbon sugars, are not converted to CMF, but the furfural is being produced in high yields. And then you go to the next reactor, and then you basically increase the temperature and get all the CMF, and voila, you have a process. So this is also a little bit, basically, reactor design. We did a lot of work. We found out, well, a classic. We were moving from batch reaction. The yields were good, but when we moved to semi-continuous reaction, which is basically replicating a little bit of a CSTR, what we were doing is replacing the organic phase every hour and see if that would increase the yields. And you can see that the first hours, the CMF, most of the CMF is produced and extracted in the organic phase. And in the last hours, still a little bit comes out, but these were really the best yields that we could get. We did a lot of statistical analysis. We modeled the reactions. We did a lot of things here. It was an infinite amount of experiments and modeling the reaction and iterating on it. Why? Because we wanted to have a good model of the reaction to try to predict where are the best yields or conditions, sorry. What could be the best conditions for our process? We wanted to break the limit. And after thousands of experiments and iterations of the DOE, the design of experiment, I thought it was very interesting. I really liked it because the prediction that you see here at the bottom as temperature that you need to use, reaction time, polarity of the organic solvent, the stirring rate for our specific system that we had in the lab, the organic solvent fraction, the amount of organic solvent that we would put, these combinations of the bottom, well, basically, this was the system saying, why don't you try this? You're going to get higher yields. And indeed, we got 96.7 CMF from this process, and it was the highest in literature. Again, we thought, hey, 1 point, what is that? But no, it's really, everything was above 96%, and it's literally the best in literature. So that was this was an example of hard work pays off. It was literally years of experimentation. And finally, the conclusions, I think I did it pretty quick. As you can see, there is great potential in second-generation biomass. I did not want to enter into detail, but the phase that we are entering now is that we are using a cotton textile, waste textile, because basically there is a lot of tons of waste textile nowadays that are incinerated because no one can do chemical recycling of that. And we are testing the process, it's working very well, and we are going to focus on that. Well, as you can see, different furanics are excellent platform chemicals for this purpose. The combined CMF and furfural production from biomass is possible at high yields in biphasic systems. And of course, yeah, the reactor design is very important. Statistical analysis is one of the most important things I emphasize are steps forward to improve the lab scale results. And that's it. Thank you very much.
We have time for a few questions.
Can I put my slide now? Sorry. Thank you, Jorge, for the nice talk. I was wondering about the chlorobenzene. So, what about the price? Is it expensive? No, because the amount that you are needed for that.
Yeah. Chlorobenzene, that was a very long conversation. First of all, halogenated solvents are not the best. But in this particular solvent in the pharma industry is used a lot, so we had the green line. The money is not so bad, it's not so expensive because again, it is so extensively used in the pharma industry that there are competent prices. But in particular for this process, because the organic solvent is recycled all the time, and it does not get, we don't lose it. It doesn't decompose for the conditions that we use. So we use it for a very long amount of cycles. Every now and then we need to refresh, and that's it.
Okay, and what about the humans formation?
There are not so many humans formations in this process. There are not so many. Because in the formation of CMF for this, well, as you can see, the yields were 96.7. Is very, very optimized for lab scale, and the amount of humans is very low. It is true that we need to filter them out from the aqueous phase. So maybe I can quickly, here, in the aqueous phase, what you see in the end, if it's not running in optimized conditions, is of course some humans. But in the process, in the pilot scale, we have a filtration step that so far works well.
Thank you.
Thank you for the presentation, very nice. My question is more on the downstream processing of the furfural or the CMF, because you have an organic extraction.
Yes.
And when you are working with the lignocellulosic material, do you have problems for the purification of the CMF or the furfural?
Thanks for the question. No, so far no. It's not so troublesome because in the chlorobenzene with the CMF and the furfural, this mixture is quite easy to distill. It's quite easy. It's a distillation that works well. But now that we are facing the construction of bigger materials for the plant, it's definitely conversations that we are having right now. Like how much we can believe that everything is going to go as well as we see. Because other fractions can end up there sometimes, especially when you come from lignocellulosic materials. Wood has so many different chemicals in it, even depending where the wood comes from. Sometimes it has metals residues or things like this. Yeah, it's definitely in conversations. But so far it's working fine with a simple distillation.
Hi, thank you for the nice presentation. On this particular slide, you actually said something about nucleophilic substitution. So I see the solvent that you use is chlorobenzene. So it might have an affinity for HCl. So from where, what is the source of the nucleophilic substitution? Is it the solvent or HCl?
It's a solvent. So the chlorobenzyl HCl does not like to be in the chlorobenzene phase because it's completely miscible with the water. It has very good immiscibility, so the HCl without the water, it does not go there. There are traces. And the substitution, the nucleophilic substitution happens in the aqueous phase, and it's the HCl because the concentration is so high. It's just so high. It's not so favored, but the concentration of the solvent is just too high, so it happens there.
And just a follow-up question on that. Are you looking into some other solvent other than chlorobenzene?
Definitely. You know, the design of experiment that we used there, one of the parameters was the polarity. That is very simplified. It's actually the Hansen parameters. It's a combination of different, what we know. There were a huge list of solvents. There are others that gives even slightly better yields, like for instance fluorobenzene. Somehow it's just better, slightly better, but fluorobenzene is a no-go.
Very inspiring. Thank you very much. Very inspiring lecture. But I'm still worried about the use of concentrated HCl for two reasons. The one is material of construction, so corrosion.
Yes.
And the other one is building of traces of chlorine into your product that will eventually end up in your path. Can you comment on those two issues?
Yeah, definitely. First, materials of construction. That's the reason why in the 20s they couldn't do it. As simple as that. They couldn't do it. But nowadays it's becoming easier. It's become one material of construction that we use everywhere there is a plastic plant. It's PVC. PVC is inert, completely inert, and not just inert, cleaner, and in years is still intact. That's the first thing. The second one, the traces. That is true, that I'm going to get back to here. But there is a separation. So when we produce MMF, we produce MMF also in very high yields because it's a very, very easy, simple reaction that is in literature for many years. Occurs at room temperature. You only need to mix the CMF with methanol at room temperature and you have a full conversion. Like we are talking 96 plus again. It is true that some of it stays there, and the steps between the MMF and the FDCA, which is the intermediate, is monitored, is heavily monitored. We are working on that right now, because the ACL is indeed stays there in small traces.
That's part of this second answer. For the PVC is great. The second was part of the answer, the substitution, I can see it. But the level you are working, I could imagine having chlorine built all over the place into the molecular structure, just in ppm level.
Yes.
But ppm level could be enough to kill your product quality. So you could put a chlorine having electrophilic substitution at a carbon 2 or 3.
Yeah. Yeah, you're right. You're completely right. But there is one thing that maybe it brings some light. The formation, the step of MMF to FDCA is a cocktail of catalyst, and it requires HBr. So we are looking into how we can do it with ACL, because we need an acid for that. It's a step that needs an acid. And the acid is taken care in between, so after the FDCA. So I think the solution will be to see how we can make that cocktail with ACL. And now that you say this, another thing that we are looking into is BMF, because it uses HBr. And then it would be like a no-brainer, you know, like we have already HBr we need HBr for FDCA, and we know how to take care of that after it. So that could be an alternative.
Thank you.
Is there any more questions? So it seems to be the end of the session. Do you want to?
Well, thank you very much, Jorge, for the last talk. But well, this sets the end of the meeting today. Well, it's been a long day, but very nice, at least for me. A lot of inspiring talks. I want to thank the external speakers. I did bring a small gift, so maybe if you could maybe come, or maybe Xavier, can you help me, because I'm holding the microphone. So some small chocolates for the external speakers. Of course, I forgot to give it in the moment, so I realized halfway that's about the excitement I had in the morning. Well, I think we started today with the opening by André saying whether there is hope or not, and I think the answer is that there is hope for biomass. Yes, so your son can keep on dreaming. But also, we have also been seeing today that lignocellulosic feedstocks are increasingly becoming important. We really need to step up. We have seen furfural as a very important intermediate molecule, so with a lot of developments. Last one, also a good example, but already in the morning, of course, HIGFLY, we have seen it. Jean-Paul Lange also showed us. So furfural, a very important molecule. Also, biorefining, a very important approach to valorize everything, and co-production, as we also saw with Fabiola. Well, these are my take-home messages. We really need to keep on working on this. So I hope the answer and the spirit remains. Well, with this, I want to end. Finally, just as a side note, we have arranged some drinks, but they will take 15 more minutes because Jorge was pretty fast. And so I hope some of you at least can stay and join us for some drinks, and otherwise stay connected. We have recorded the event, and we will put it on YouTube for you to watch it afterwards, and also some other people that really wanted to be here but couldn't. And well, that's it from my side. Thank you very much, all of you, also for your presence today. Thanks.